Quantum signals travel at least 10,000 times faster than the speed of light. Researchers at the University of Geneva verified this phenomenon with 99% statistical confidence. However, Albert Einstein called this spooky action at a distance because it threatened your fundamental understanding of reality. On May 15, 1935, Einstein's 4-page paper landed in the Physical Review like a hand grenade. This single document launched a 50-year war for the soul of modern physics. To understand the magnitude of what happened that year at the Institute for Advanced Study in Princeton, you have to picture the scene. You've got Albert Einstein, the man who'd already ripped up the rulebook of time and space once before, looking at his younger assistants, Boris Podolsky and Nathan Rosen, with a mix of triumph and deep intellectual trepidation. They had found the ultimate logic trap. For over a decade, Einstein had been it's one of the great ironies of history. The man who won his Nobel Prize for explaining the photoelectric effect, a cornerstone of quantum theory, couldn't stand what his creation had become. He'd spent years locked in a monumental battle of wits with Niels Bohr, the director of the Institute for Theoretical Physics in Copenhagen. During the 1927 Solvay conference, they'd sparred in the hallways and at breakfast, Einstein famously declaring that God does not play dice, and Bohr, ever the philosopher, telling Einstein to stop telling God what to do. But by 1935, the EPR trio wasn't just arguing over breakfast anymore. They were challenging the very definition of what we call real. They formulated a thought experiment to prove that if quantum mechanics was a complete description of reality, then the universe was fundamentally spooky. Einstein's problem was with what Bohr called complementarity, the idea that a particle doesn't have a definite position or momentum until it's measured. Einstein felt this was nonsense. He pioneered the idea of realism, the common-sense belief that physical properties exist, whether or not a human is there to see them. He also believed in locality, the principle that an object can only be influenced by its immediate surroundings. The EPR paper was his attempt to show that quantum mechanics forced you to give up one of these two pillars of sanity. It was his ultimate manifesto for a logical, deterministic universe, written by a genius who refused to accept that the bedrock of reality could be built on a foundation. To understand what Einstein was so bothered about, we have to look at what he called elements of reality. Now think about a coin. Not just any coin, but a multi-million-dollar coin flip happening in the dark. In our everyday world, if I flip a coin and cover it with my hand, you know it is either heads or tails. It has a definite state. That is what Einstein called realism. The object possesses its properties regardless of whether we are looking at it. But Niels Bohr and the Copenhagen crowd were saying something far more radical. They claimed that until you lift your hand, the coin is not heads or tails. It is a blurry, ghostly mixture of both states at once. Einstein hated this idea. He famously told Max Born that God does not play dice, but his real objection in the 1935 paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" was not just about the gambling. It was about the spookiness of how that dice roll affects the rest of the universe. To understand the core of the 1935 EPR paradox, we have to examine the mechanism of entanglement. Imagine we take two particles and entangle them, a term Erwin Schrödinger would soon coin, but which Einstein, Boris Podolsky, and Nathan Rosen were already dissecting at the Institute for Advanced Study in Princeton. In this state, these two particles share a single mathematical identity, a single wave function. Now imagine we pull them apart. We keep one in a laboratory at Princeton, and we ship the other to the Andromeda Galaxy, 2.5 million light-years away. According to the rules of quantum mechanics, If these particles are entangled, their properties are inextricably linked. If one is spinning up, the other must be spinning down. Here is where the ghostly part breaks the brain of any classical physicist. Einstein pointed out that if you measure the particle in Princeton and see it is spinning up, you instantly, and I mean instantly, know the particle in Andromeda is spinning down. This posed a terrifying dilemma. In Einstein's universe, nothing, not even information, can travel faster than the speed of light. That is the principle of locality. But if the measurement in Princeton determines the state in Andromeda across millions of light years in a 0-second interval, then something is fundamentally broken. Either the particle in Andromeda already knew it was going to be spin down, meaning quantum mechanics is incomplete and there are hidden variables we have not discovered yet, or the universe is non-local, allowing for what Einstein called spukhafte Fernwirkung, or spooky action at a distance. And that's when the real question emerged. Einstein, Podolsky, and Rosen were not trying to say quantum mechanics gave the wrong answers. They knew the math worked with incredible precision. What they were arguing in Physical Review Volume 47 was that the theory was their definition of reality was very specific. If, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Since you can predict the Andromeda particle's state by measuring the Princeton one without ever touching Andromeda, that state must have been fixed long before the measurement. Think of it like a pair of socks. If I put the red sock in one box and the blue sock in another, and I send one box to you in Paris while I stay in New York, the moment you open your box and see the blue sock, you know I have the red one. There is no magic. No signals were sent between the boxes. The reality of the sock was determined the moment I packed them. This was Einstein's hidden variable theory. He believed the particles were like those socks, carrying secret, but Bohr disagreed. Bohr insisted the particles were more like a single coin being sliced in half while it was still spinning, only becoming heads. Einstein found this preposterous. He spent his final years at Princeton, often walking with Kurt Gödel, trying to find a way to preserve local realism. He could not accept a universe where things do not exist in a definite state when we are not looking at them. For Einstein, the moon was still, but the quantum world seemed to be whispering a very different, much more unsettling story about how the fabric of space. For nearly 3 decades, the EPR paradox sat on the shelf like a powerful, unexploded bomb. Most physicists in the 50s and early 60s treated it as a philosophical curiosity, a ghost story for old men like Einstein to grumble about while the rest of the world got busy building transistors and lasers. They figured if the math works, why? But in 1964, a quiet, red-headed physicist from Northern Ireland named John Stuart Bell decided he wasn't satisfied with just shutting up and calculating. He was working at CERN, the European Organization for Nuclear Research, but he took a sabbatical to the United States, spending time at Stanford and the University of Wisconsin. It was during this period of reflection that he did something no one thought possible. He turned a metaphysical shouting match into. To understand what Bell did, you have to appreciate the theoretical minimum of the argument. Einstein believed in local realism. Realism means things have properties even when you aren't looking. The moon is there even if nobody is watching it. Locality means that if I do something here in my office at Stanford, it can't affect you in London faster than a beam of light can travel between us. It's common sense, right? Einstein argued that for quantum mechanics to make sense, there had to be hidden variables. Think of it like a pair of shoes. I put the left shoe in a box and send it to Mars, and the right shoe in a box and send it to Venus. When the astronaut on Mars opens his box and sees a left, he instantly knows the shoe on Venus is right. There's no spooky action there. The shoes were always left and right-handed from the moment I packed them. They carried a hidden variable, their handedness, with them. But Bohr and the quantum camp said, "No, John, the shoes are neither left nor right until someone opens a box." To Einstein, that sounded like lunacy. Bell, however, realized that if Einstein's hidden variables actually existed, there was a strict mathematical limit to how often those two shoes, or particles, could agree with each other if you started measuring them at weird different angles. He developed what we now call Bell's inequality. He proved that if the world is truly local and real, a certain number, let's call it the correlation value, cannot be greater than 2. If quantum mechanics was right, and the particles were truly entangled in a way that defied space and time, that number could go as high as 2.8. Everything they believed up to this point was wrong. Bell had drawn a literal line in the sand of the universe. On one side stood Einstein, common sense, and the idea that the world is made of independent things. On the other side stood the spookiness of quantum mechanics, suggesting a universe that is fundamentally interconnected in a way that bypasses the speed of light. This wasn't just a chalkboard exercise anymore. Bell's paper on the Einstein-Podolsky-Rosen paradox, published in the short-lived journal Physics Physique Physica, essentially told the experimentalists, "Go find the answer. Stop arguing and start measuring." He had laid the trap for reality itself. If someone could actually perform this experiment, measuring entangled particles at different angles and comparing the results, they could finally prove whether Einstein's ghost was a figment of a brilliant man's imagination or a fundamental truth of our existence. He had transformed Einstein's thought experiment into a real experiment, setting the stage for a 50-year battle in the lab that would eventually challenge our very definition of what it means for something to exist.